Very good morning. Welcome you all to the NPTEL course on Economic Operation and Control of Power System. And today we are going to talk about Optimization Preliminaries, means Fundamentals, section 1 of lecture 4. So importantly, when we are talking about power system, most of the mathematical representations as well as equations, they are not purely linear. Sometimes they are linear, sometimes they are non-linear. As well as we need to optimize the overall cost of generation to meet the required load. So when you talk about optimally utilize the generations to meet the load, that means we need to understand optimization. So probably the detail of optimization, direct application to power engineering, we'll talk in due course of time. But before that, we need to understand what is optimization and how that can be applied to economic operation and control of power system course. Now, when you talk about optimization, let me go back to your plus 2 fundamentals. So during plus 2, we have been taught that a function is to optimize any function, we take a function f of x, then we differentiate equal to 0. Then we go for second differentiation, and then we substitute those values. If it is positive, then that point is minimum. If it is negative, that point is maximum. That is what actually has been taught to us during school days. But now the scenario is almost same fundamental, but we need to address many more complicated problems today. Now, optimization process aims to minimize or maximize a certain objective to achieve most optimal but feasible solutions. Now, you need to have a function which is normally called as objective function, and that objective function could be a linear or nonlinear function. Most likely it is nonlinear, and that need to be either minimized or maximized. Now, we need to have different limits imposed on the optimizing process are called constraints. For example, if I'm interested to know the generation output of a particular power plant, that is P, and that value of P must be less than its maximum generation and more than its minimum generation. Okay, so many times I have told you that if there is a cost characteristic, for example, so just what I will do, I'll just demonstrate it. So if this is going to be my cost characteristic, and if this is my P minimum, and this is my P maximum, so probably within this range, you have to change your P. So to me, the P max is the maximum limit and P min is the minimum limit, and hence that is my constraint. So P must be, I can rewrite that P must be less than or equal to P maximum and greater than or equal to P minimum. All right. So this is the equation is known as my constraint equation. Okay. Now similarly, we can also find out the region bounded by constraint is known as feasible region, the area within which, for example, if a space is given to you, you can identify a zone in which my optimal point lies. Okay. So that is my region bounded by the constraint is known as feasible region for the optimizing process. Now, optimal solutions should lie at the border of a feasible region. Means ideally, they do occupy a point which is mostly at the extreme point because you optimize it. Now, local optima is a very common term because there are few functions which are keep on oscillating and probably they are not convex functions. Let's say if I do talk about a function, all right, which is keep on oscillating. And in that, if this is my point of operation, the gradient at this point is certainly at that optimal point is going to be 0 because it is just a constant point to me, and the tangent which is different there. So at this optimal point, the differentiation of any function equal to 0. There is no doubt about it. And that is also true at this point. That is also true at this point. That is also true at this point. So you'll find many points where my differentiation equal to 0 or the gradient is something different. Now what happens if I take the starting point of my optimization is x, then probably it will keep on moving, and the moment the gradient is 0 or the differentiation is 0, it will say, oh, you have reached your optimal, and the program exit. Okay, so it will tell you the optimal point is, this is my x dash is the optimal point. However, there is another optimal point which is lying here, all right? So that is not visible to this fellow because the starting point has chosen in such a manner that it lie down at this point and accept, oh, this is my optimal point. So this is my some sort of optimization, but it is known as local optimal. Okay, but if you find many local optimal points, if I would have started from here, I could have got this point. If I would have started from here, I could have got this point. So now what is happening, depending upon your starting point, you get an optimization point, but which is not necessarily to be optimal. So that is my local optimal. But if you take all the local optimals of your function and then take the best out of which will give me the global optimum. So global optimum is defined as the point whose objective value is best among all the points present in the feasible region. And also, the constraint functions and simple variables limit are lumped under the term constraint, so everything can be put in a constraint form. And if the constraints are such that no such region exists, means if I do say that my P is of range A to B, and I'm not getting any solution within that range, so probably I'll say there is no solution exists, which means that there are no values which satisfies all the constraints. So it may so happen, I may tell that, okay, just for an example, the range within which you have to find a point probably do not lead to an optimization, and that is possible, and hence we say there is no feasible solution, there is no reason exists to carry out optimization. Now, optimal problems, they are different types. One is unconstrained and the second one is constrained. Unconstrained means the whole space is yours and you choose a point which is less likely in a practical problem. So practical problems are always constrained, but in textbook for our understanding we solve unconstrained optimization for learning constrained optimization. So before you get into constrained optimization, you need to understand what is unconstrained optimization. Now, there are different type of unconstrained optimization problems. One is single variable or could be multivariable. And those multivariable optimization problems and single variable optimization problems could also be having equality constraint, and it can also have inequality constraints. Equality constraint means I may say my variable y, which is equal to 5, or I may say my variable y, which is greater than or equal to 5. So now what happens? It could be one is equality, the other is inequality. Okay, and the function could be f of x, which is x square plus 3. Is a function, okay, which is a nonlinear function. And if I do not have any constraint, only I have to optimize this function, then that is my unconstrained optimization problem. But if I have to do this and put the variable, for example, f of x equal to x square plus 3, and x must be less than or equal to 5, so then that optimization problem becomes a constraint optimization problem of single variable. I can also have f of x, which is x1 square plus x2 square plus 25, where x1 is less than or equal to 3 and x2 is greater than or equal to 5. So now it is a multivariable inequality constraint optimization problem. All right. So you can find many problems of this order. Now to start with, as fundamental, what do you understand by unconstrained single variable optimization problem? So it is simple. So you have a single variable which is x, all right, and the function which is f of x. So first of all, what you need to do, you have to differentiate and equal to 0. That means if the objective function is f of x, you have to differentiate, which is f dash x need to be equal to 0, f dash equal to 0. You can see from equation number 4.1. But now the question is, when you make that equation equal to 0, how do I find the minimum and maximum values? That is the question. Because f dash x equal to 0 does not guarantee that you are at optimal point. But even if you are at optimal point, it does not once again assure you that are you at actually maximum point or minimum point. For an example, if I draw a characteristic, all right, now at this point my f dash x equal to 0, at this point also that f dash equal to 0. Now my question is, this leads to a minimal point and this leads to a maximum point. All right. So you need to identify. So first condition, f dash equal to 0, means you are going to reach to an optimal point, but you need to identify whether they are minimum or maximum points. Now for that, what you need to do, you need to identify whether f dash x, f double dash x up to f n x exist, and then f dash x, f double dash x up to f n minus 1 x equal to 0. And the last differentiation, that is the nth differentiation, must not be equal to 0, then the following conclusion can be made. So if the last differentiation, that is the nth differentiation of the variable x, if it is not equal to 0, that means it is either positive or negative. If it is positive, then you are leading to a minimum point, and if it is negative, then you are leading to a maximum point. However, if n is odd, however the n is odd, and then x is a point of inflation, okay, and that is very important, because for even differentiation you can get maximum minimum, but when n is odd, then the point x is leading to an inflation. We'll see a small example. Next slide. Let us consider one simple example, equation 4.2. F of x is x to the power 5 minus 5x4 plus 5x cubed plus 5, and optimize it, okay? So this is a kind of assignment you can take up. And what you have to do, first you differentiate simply, and 4.3, as you could see, it talks about 5x square into x minus 1 into x minus 3. If I make this equal to 0, what will happen? That means x equal to 0, I'll get three values, x equal to 0, x equal to 1, and x equal to 3. Is it okay? So now when x equal to 0, you go for second differentiation now. So that is been given to in equation number 4.4, and you differentiate and substitute the value of x equal to 0, you get second differentiation 0. And then if you put the next value x equal to 1, you will get another value. When you put x equal to 1, so probably this is going to be 20 minus 60 plus 30 is equal to minus 10, which is less than 0, and hence x equal to 1, the point which is my maximum point. Similarly, if I put x equal to 3, the answer is actually 210, which is greater than 0, which is positive, and hence it is the minimum point. So it has been given in a small box, as you could see, that by substituting x equal to 1 and x equal to 3, you get a negative value and you get a positive value, and that shows which is the maximum point and minimum point. Now similarly, if I extend this problem to a multivariable, it is unconstrained but multivariable. Instead of one variable, you can have multivariables. I will just tell you what is the importance. You may be surprised to see it is a coarse and pass system, economic operation, control system, and we are talking about optimization. My dear friends, when you try to solve a problem, there are thousands of generators, and those generators, you need to find the optimal power output of each generator, all right? And there are P1, P2, P3 up to Pn, so it becomes a multivariable problem, okay? So you cannot optimize one generator and say I have achieved optimized solutions. No, you have to optimize not only P1, but you have to also optimize P2, P3 up to Pn, and hence all the power system optimization problems are constrained multivariable problems, constrained as well as multivariable. So now we are focusing on unconstrained multivariable. So similar to unconstrained single variable, you can solve the problem for multivariable, where you have to take the partial differentiation dou f of x upon dou x1 and dou f of x upon dou x2, as well as dou f of x upon dou xn need to be made equal to 0. Okay, so it is a partial differentiation concept, and you will also try to understand the sufficient condition for minimum or maximum is similar to what we have discussed. Now it says that assuming all the partial derivatives of f of x up to the order k to be existing and continuous, so in the neighborhood of a stationary point x, if my d of f of x equal to 0, all right, but d of f of x is not equal to 0. So this is my rth differentiation and this is my kth differentiation, all right? Similar to the first and second difference. This is the rth differentiation and kth differentiation. Then the following holds good. But it says if k is even, x is relative maximum if dk of f of x is positive. Similarly, if k is even, x is relative maximum if dk of actually x is negative. So it is the same thing that k need to be even. If it is positive, leads to minimum. If it is negative, will lead to maximum. But if dk of f of x equal to 0, then you cannot say it is maximum or minimum. It is something different. Now if k is odd, then x is not an extremum, okay? And if dk of f of x takes both positive and negative values, then x is a saddle point, which is a very, very boundary oscillating point of optimization characteristics. Now, when you talk about constraint optimization, I want your attention here very seriously, because all our problems in power system that we're going to discuss are constraint optimization problems. So the one important part is method of Lagrangian multiplier is being used to handle constraint optimization. I will tell you what is constraint optimization, how it has been handled. Now let's say I do have a function f of x, which is known to me, and then I do have some constraints, okay? So f of x is my function, objective function, and whereas actually constraints, let's say they are actually, kind of actually beta of x, for example, okay? So this is objective function and this is my constraint. Now, when you optimize, you need to have a single function which need to be differentiated. So what you ideally do, this constraint function beta of x being merged with f of x through a multiplier. So you have the objective function f of x plus a multiplier times beta of x, okay, become my objective function. All right. So then you are accommodating those constraints into your objective function through a multiplier, and mostly it is known as Lagrangian multiplier. Okay. So let us first concentrate on a problem of minimizing a function of two variables x1 and x2 with one equality constraint. We will then generalize the method for any number of variables. Okay. To understand first actually two variables and one constraint. So what are those variables? x1 and x2. So what I'm supposed to do? I'm supposed to minimize a function f of x1 and x2 subject to the constraint g of x1, x2 equal to 0. Alright. So you have an objective function that need to be minimized. Alright. And there is a constraint, equality constraint, where a mixture of x1, x2 relationship equal to 0. Now what you do? Simply differentiate dou f upon dou x1 and similarly dou f upon dou x2. There are two variables. If there are n variables, you have to differentiate n times. But for two variables, you have to differentiate 2 times. So after differentiation, you equal to 0. And then the first differentiation, once you get it, df or dou f, that is dou f upon dou x1 into dx1 plus dou f upon dou x2 into dx2, which is equal to 0. Now the constraint g of x1, x2 is always maintained, and hence we can also do it dou g, which is dou g upon dou x1 into dx1, dou g upon dou x2 into dx2 equal to 0. And assuming that dou g upon dou x2 is not equal to 0, that is the constraint optimization. So probably the same equation can be expressed as dou f upon dou x1 minus dou g upon dou x1 upon dou g upon dou x2 times dou f upon dou x2 into dx1 equal to 0. So this is the simplified version. And since dx1 can be chosen arbitrarily, one can get the following after rearranging this equation you can launch at the end. Now, without delay, what we need to do, a quantity lambda is now defined. What is lambda? Lambda is a constant which talks about dou f upon dou x2 upon dou g upon dou x2. Okay, so this is what the lambda we have considered. And when you substitute this value lambda, my original equation that we have discussed, okay, now just a minute, just if I go to the previous one, that 4.16, okay, 4.16. So this is this equation is basically 4.16. Okay, can be now rewritten as dou f upon dou x1 plus lambda time dou g upon dou x2 equal to 0. So this is a very, very important expression for two variable constraint optimization equation. So what you have to do the objective function with respect to x1 variable plus lambda time, the constraint with respect to x2 variable now equal to 0. So finally, one can also rewrite that the equations, the overall equations now can be represented as L of x1, x2 lambda. Why we say x1, x2 lambda? Because it is two variable x1, x2, but lambda is also a variable. Okay, so totally there are three variables. In a two variable problem, you will have three variables including lambda, which is nothing but my objective function f of x1, x2 plus lambda times g of x1, x2. So this is the objective function with Lagrangian multiplied. Now, if you talk about a simple unconstrained optimization problem, you can solve many problems. That is f of x1, x2, which is given as 0.25 x1 square plus x2 square. And you can solve this problem easily by taking different variables, and you can differentiate with respect to x1 and x2 equal to 0, and then you get the gradient of that equation, and then you can get the optimization value for both x1 and x2. Now, when you try to minimize a linear equation, just for your understanding, because I thought of just touching upon all the solution processes available for optimization for your own benefit, but we are not supposed to get too much detail into the optimization course here. But for your own benefit, if you like to minimize a function which is 0.25 x1 square plus x2 square with a constraint of omega times x1, x2 equal to 0, so then where omega x1, x2 equal to 5 minus x1 minus x2, so now we need to optimize this equation subject to your x1, x2 satisfy this one. Means if I rewrite it, so this is nothing but 5, which is equal to x1 plus x2. So the condition is that you optimize the original equation 4.24 subject to x1 plus x2 is always 5. So it could be 4 plus 1, 3 plus 2, 2 plus 3, 4 plus 1 and 5 plus 0. Any option is available. So you could see through that actually you get a function where f equal to x1 equal to 4 and x2 equal to 1 and provides you the maximum value, and you can substitute. So 4 square into 0.25 is 4 and 1 square, so the objective function is now 5. So f of 5 is the function with x1 equal to 4 and x2 equal to 1 satisfies the maximum point. So that is how actually the optimization problems are solved, and probably I'll just take you go through the different type of problems available to you. So you can perhaps actually identify the gradient vectors of any function, and that will give an idea where the optimization points are lying. So I'll move further and then just to, yes, so we'll try to solve a simple problem for our benefit. So equality constraint simple optimization, one numerical example let us solve. So in the graphical method we saw how the solutions are lying at 4 and 1, but now let us solve through Lagrangian multiply. So what has happened, what is my objective function? 0.25 x1 square plus x2 square, and as I told you lambda times the constraint. So if my constraint was x1 plus x2 equal to 5, I can say 5 minus x1 minus x2 equal to 0, and that is nothing but this constraint. Okay, so now you have a function with you. So what you have to do, you have to differentiate. So there are three differential values. One is actually dou L with respect to, you have to differentiate with respect to x1, then you have to differentiate with respect to x2, then you differentiate with respect to lambda, because there are three variables. So three variables and three equations. Okay, what are those equations? As you could see, the first equation gives you 0.5 x1 minus lambda equal to 0, 2x2 minus lambda equal to 0, and then 5 minus x1 minus x2 equal to 0. So there are three equations and three variables, and you have to solve, and the solutions are x1 equal to 4, x2 equal to 1, and lambda equal to 2. So probably you could see either you use Lagrangian multiplier, or even you from this equation, linear equality constraint equations, you could see that they both are satisfying. So, but in power system, we'll try to solve most of our equations through this equation. Okay, I will just try to emphasize a little bit here. In power system engineering, what happens, this x1 and x2 are nothing but majorly my variables P1 and P2. Okay, P1 and P2 are nothing but the power output of the plant 1 and 2, and it can go as maximum as Pn. And what are the constraints? Constraint means, for example, P1 plus P2, for example, equal to 300 megawatt. So I want to meet the total power of 300 megawatt out of two generators. Okay. So then you can form this equation that P1 plus P2 minus 300 equal to 0. So that will appear in this zone, and the objective function is nothing but my cost characteristics, which are non-linear. So they are ideally AP square plus BP plus C, and similarly it could be P1 square, BP P1C, or sometimes it is P2 square plus BP2 plus C. So they are non-linear equations will come in this zone. Okay. So you have cost characteristics of the power plant to generate P amount of power, how much money you have to spend. So my objective function will be now the summation of the cost characteristics of cost functions plus lambda time the constraint, and that will help me to understand what is P1, P2, P2. So once the objective function are known to me, the constraints are known to me, I can easily calculate the value of power output of each and every power plant. And that's why it is important for you to understand what is simple optimization with equality constraint, with multi-variables. All right, then you can have many more complicated problems. This is just a journey for all of you, and additional equality constraints. So I request all of you to get into mathematical optimization sections or any optimization textbooks, linear optimization, nonlinear optimization. You can focus on to know much better on these subjects. So this is how the inequality constraints are being satisfied. And then what is inequality constraint? So inequality constraint means you could see, now previously used to say GIX which is equal to 0, but now we are saying that GIX is less than or equal to 0. And then how do you handle it? For example, if I say my MVA flow in a particular line is less than or equal to 100 MVA. This is the line I. So this is some sort of my inequality constraint. Okay, that also can be incorporated in our optimizing problems. So then we talk about Kuntukur conditions, and then there are different applications of those equality constraints. And this is how the problem when we talk about inequality. So you could see that this is my objective function, and there is an equality constraint as well as there is an inequality constraint. So how do you optimize a function which has an equality constraint as well as inequality constraint? So you could see the functions, which is my equality constraint characteristics. All right, and then I have the inequality cost function characteristics, and then probably satisfying those both, I have to find my optimal points. All right, so you can take one numerical example. So what you have done, for example, if this is my objective function and this is my equality constraint, it's the inequality constraint. So instead of lambda, I have added one more variable, that is mu. Okay, so the first condition with equality and inequality constraints are the dou of L upon dou x1 must be equal to 0, dou L upon dou x2 must be equal to 0. These are the two immediate differentiation. And then the second condition is 5 minus x1 minus x2 equal to 0, that is differentiation with respect to lambda. And then the third condition, which is going to be this one. And the fourth condition, which is very interesting here, that the mu of this must be equal to 0. So how do you solve? That is the bigger challenge here. So the first, you have to find a solution with a test possibility. So you have to substitute mu equal to 0, and then you get three solutions like x1, x2, lambda. Okay, and then you can keep on changing the value of mu to different values, you get different solutions, and then when all the conditions are met, then you conclude what is the value of solution. So here the solution, optimal solutions are not easy as similar to your equality constraint. So when you get into inequality, so there is a iterative method through which you will get your value of x1, x2, lambda, and I strongly I recommend all of you to get into wonderful textbooks and the examples of Oldenburg and some other optimization textbook to understand both equality and inequality. But nevertheless, I tried my best to make you understand how to obtain those solutions when the nonlinear optimization with equality constraints as well as inequality constraints. Thank you very much.